Right, ladies and gentlemen, good evening and welcome. Welcome to the third evening, already the third evening, of the Wright Colloquium for Science, the 21st edition, which will run until the end of this week. Thank you for joining us this evening in the Piaget Auditorium at the Uni du Four, Geneva. And thank you to all the people who are following us online remotely. For those who have been with us since Monday, you now know me. I'm a science journalist. I'm Sarah Sermondada, and it's a pleasure for me and an honor to accompany you this week to moderate the discussions post-conference. Now, by now you know how it works. Every evening we welcome one of our top scientists to lead us through this journey through symmetries of the universe. So tonight we are going to talk about one of the biggest enigmas of contemporary times, the imbalance in the universe between matter and antimatter, which should have been created in equal quantities by the Big Bang. So where could the antimatter have gone, and what experiments are being carried out today to answer this important question? So on this topic, we are delighted to welcome Yasmine Amhis. She is head of research at the CNRS, French Research Laboratory, at the Irène Curie Infinite Physics Laboratory in France, and she works on experiments at CERN involving antimatter, and particularly that on the LHCb experiment. Before that, a quick reminder of how the evening will unfold. The evening will be divided in two parts. So first of all, we have the scientific talk, of course, that is going to take about 40 minutes, given by Professor Yasmine, and then we will have a panel discussion where you will be joined by two other speakers of the week, whom I'll introduce later. This will broaden the discussion, I hope, and provide some interesting insights. So this question and answer session will last around 40 minutes as well. And I'd like to remind you that there are two ways for you to ask your questions. First, the traditional way is by requesting the mic if you're in the room. And the second, at a distance, so remotely, you can use the Slido platform, and for that you need to scan the QR code that is on the screen right behind me. And you can put your questions to us even during the conference through this online app. And you can ask your questions in French and English. They will be translated by our team of interpreters, and please use a headset if needed. Finally, I'm going to ask you to not put your volume of your headset too high, not to disturb your neighbors. And if you are online, then you have access to both languages as well. Finally, please put your phones on silence or turn them off in order to respect our speaker. And last but not least, I'm now going to welcome scientists from the University of Geneva, who is going to present Yasmine Amhis. So we have Anna Svirla this evening from the Department of Nuclear and High Energy Physics. Anna, welcome. Good evening, everyone. It's a pleasure for me to be here to welcome you and present Yasmine Amhis, head of research at the CNRS, and a passionate physicist who explores symmetries in particle physics. The career of Yasmine in particle physics is a true testimony of her technical expertise that is exceptional, and all the academic realizations and achievements that she has made, as well as her leading role in the scientific community. Yasmine was born and grew up in Algeria. Her academic studying started with a PhD in experimental physics in Paris Sud in 2009. Back in the day, she was already exploring research fields that were essential, and she was concentrating on the disintegration of particles within the framework of the LHCb at CERN, a study that potentially or could potentially reveal the links between particles and antiparticles. After her PhD, Yasmine went on to pursue research at the École Polytechnique Fédérale de Lausanne, and in 2012 she obtained a position at the CNRS at the Research Center in Quai d'Orsay, where she continues to deepen and widen her experience and research in the field of symmetries and beyond. Throughout her career, Yasmine has played a leading role at CERN. For example, in 2022, she was elected scientific coordinator of the LHCb experiment, one of the more prestigious positions in the project. And in this position, she overviewed the objectives, the scientific objectives, and the planning of the experiments for 2 years for this international project, which brings together over 1,000 scientists worldwide. So pragmatically, Yasmine works on quarks, these very minute particles that make up the nuclei of atoms. And she is also interested in leptons, another type of fundamental particle. She also studies fascinating questions about the symmetrical behavior of these particles, what we call the lepton universality. In other words, do all these particles obey the same rules, or are there differences? If she and her team detect a lack of symmetry or an asymmetry in their study, then that could be a sign of a revolutionary discovery, a new physics that goes beyond the standard model and the theory that we have today and describes elementary particles and fundamental forces, except gravity, that links them. In addition to these technical contributions and her leading role, Yasmine is highly involved in training future generations. She has supervised many PhD students, she's a mentor, and she works on standardizing and diffusing science. And she's very inspirational to the next generation of researchers. She also works on raising awareness by participating in events, by creating teaching material, and by intervening in scientific workshops at international level. Her work and her contributions have been recognized several times. She has received several distinctions and awards, among which the prestigious award, Jacques Herbrand Award from the French Science Academy, and that was in 2016. And this is an exceptional recognition in her field. Yasmine is a true leader in particle physics, experimental particle physics. I'm now going to give her the floor for her very welcome and awaited presentation. Thank you. Thank you, Anna. Thank you very much for this high-end introduction. I'm not embarrassed at all, but I'm very happy to be here. And thank you to the Geneva audience who is here on a Wednesday evening to hear about antimatter. So before diving into the deep end, I have a question for you. Have you ever heard of antimatter? Put your hand up. Oh, great. Well done. You're a great audience. That's going to make my life much easier. Second, how many of you were here for the Daniel Bowman presentation? That's not bad at all. Well done. So don't worry, I'm not going to make you pass tests or sit exams to see if you've understood everything, but we are going to use what was said as a basis. So first of all, the title is Alice's Rabbit Made of Antimatter? So this is not quite Alice nor a rabbit, but we get an idea of what I'm trying to illustrate and the notion of symmetry. So as we saw in other presentations, we saw that symmetry is very important in physics. We are going to talk about it today because it's something that allows us to explain the laws of physics and predictability, which is quite exceptional. When we explore this issue and we work on physics, there are always equations, there's always difficult concepts, but we are going to try and simplify things as much as possible this evening. And I would be very happy to know that this evening you leave with an increased curiosity on these things. Well, you're here because you're curious, but I would like to invite you to go and read things on the topic and question yourself. So how did this story begin? Well, like many other stories, it started many years ago during the Big Bang. Now, my colleagues have talked about and will talk about the Big Bang more than I will, but I'm interested in something very simple, which is the following. And this is saying when the Big Bang happened, matter and antimatter were created in an equal quantity. While when we are here today, we know that we're all made of matter and not antimatter. So we wonder and want to know what happened. Why did antimatter disappear and why are we living in a world of matter rather than antimatter? So I'm going to give you little by little information during this presentation, some examples to help you understand what antimatter is. And then what we're going to do is I'm going to give you examples of experiments that I did in order to test matter and antimatter and understand it better. So I don't know if you're lucky enough here in Geneva to have had time to go and see the great performance that is at the Museum of Art and History, the Sound and Light Show. And I thought it was great because there was something I am going to refer to this evening, a perfect illustration of the alignment of universe. So you see in this equation, it's something that we call baryogenesis. And I'm going to show you here. This is the Wikipedia page about baryogenesis, and it's what explains the conditions needed in order for matter to disappear. So without going into the detail, what Sakharov says is that for it to exist, you need asymmetries between matter and antimatter. So when there are interactions, they're not going to behave the same way. So this can be translated also in the expression that you have here, which defines the quantity and allows us to quantify what is left in terms of matter and antimatter in the universe. And we see that there's hardly any antimatter left. And we're going to try and carry out measurements in order to explain this phenomenon. So then let's move on. So one of the issues of particle physics is that there are a lot of difficult terms, and I'm going to do my best to simplify the terms. But I'm going to have to talk about symmetry. Daniel talked about it a lot yesterday. And I'm also going to have to talk about particles and their interaction. We also heard about that last night. And then we can go further. Once I finished my drawing yesterday, I probably should have called this a marmite, a big pot, as we call it for the escalade, rather than a chaudron, which is a synonym in French. So symmetry is very discrete. We see that there are several symmetries in physics. We are going to look into discrete symmetries. So first of all, there's charge, parity, and time. So if we have a particle, which is easy to imagine, if it's charged positively, then we are going to be able to compare it to one that's charged negatively. When we talk about parity, which is why we always refer to Alice in Wonderland and the mirror, is because it's a translation that's going to be the opposite. And this parity is going to be applied to an intrinsic number of quantum particles, which is also called parity. That's a little more difficult to understand, maybe, but just understand that it's a mirror image. And then the last symmetry is time, and that's even more abstract and not intuitive, is that particles can go back in time, which is difficult to grasp because we see that our clock only goes forwards. And that's when you have to try and remember that particle physics is based on quantum mechanics and restrained relativity. So the phenomena that we're going to talk about are extremely small. And when we work at this scale, then they are things that happened that don't take place in our macroscopic world, things that we don't see. So we have these three symmetries that we are going to talk about this evening. What we can then do is, according to the experiments that we carry out and what we want to test, we're going to be able to combine these symmetries differently. And that's very interesting because it's something that's intrinsically linked to the theory that describes the standard model. For example, if we can apply one symmetry, another, or again another. Now, if we apply all three together, or just two, we'll have different examples of what's going to happen. So here we are going to talk about antimatter. So we said that we could use these symmetries in order to go from an object that is positively charged to one that is negatively charged. And the oldest example is if you take an electron and you change its charge, then it becomes a positron. So there you see what's incredible of physics. When you talk about, when you work with the two communities, the positron or the anti-electron is going to be destroyed before it's detected. And this was discovered by scientists who needed solutions and was trying to resolve these issues. And a couple of years later, the positron was detected. And later on, we're going to see an example of how this positron works. It's quite interesting. So then we come to the proton. The proton, of course, you hear about. It's in the nucleus of a particle. And if it becomes antimatter, it's the antiproton. And same with hydrogen. We have hydrogen and antihydrogen. So what we want to know when we are studying matter and antimatter is these particles that seem to be very similar, how are they a little different? And how can we measure these tiny differences? So here I said we needed to talk about particle physics in order to grasp the concepts and in order to explain things that are taking place at CERN, not far from here. So how is matter organized? What do we know about it and its interactions? Well, matter is organized in the structures that you see here. It's the standard model for particle physics. And here I underline model because I don't want to forget to say something, it's a theory that enables us to explain how particles interact, how they speak to each other, and how they exchange and how they behave. And I said a model because it's a model that works very well at a certain energy level. When we work on particle physics, we work on the different energy levels because according to where we place it, we are going to be sensitive to different energies. And the standard model works very well in certain levels of energy, but we know that it's not a perfect model. So what we're going to try and do when we study matter and antimatter, it's a way of questioning this, is to say, okay, we have the standard model, that's great, but can we go beyond the standard model? So a very simple example regarding the downside of the standard model is that it doesn't explain gravity. While gravity is one of a basic interaction that we all know about. So how do we organize things? Well, we have the matter particles that are organized according to quarks and leptons, and then we're going to have the gauge bosons, who are the mediators for the interactions. So according to the particular characteristics of a particle, it will go towards one interaction or another. And why I'm saying this is because when we study difference between matter and antimatter, we can't talk about all the interactions at once. We're going to try and test gravity, for example, and then a strong interaction according to matter and antimatter, and how the particles behave according to the interaction. So just again, we have three symmetries: charge, parity, and time. And we have these groups of particles and interactions. And thanks to that, we can, in theory at least, make antimatter. So we're going to take matter particles and apply the symmetry and create antimatter. So this is just the standard model at a larger scale for you to have all the information. I thought it was pretty, so I just wanted to show you the details. Now, how do physicists work? Well, for those who do experimental physics, this is how they do. They create lots of particles. I'm going to come back to that later, and we're going to try and study these as much as possible. We're going to try and establish an ID for these particles. So the same way as we have a child and we have a health certificate, we put a size, we put their weight, etc. Here we put the mass, we put the lifespan. You see we have different formulas to write these and all its properties. And so these little books that we have here, I wanted to show you because I really liked them when I was a student. We call them booklets. I'm not sure they're still edited or published, but they used to be updated every 2 or 3 years. And every year, or every time we discovered a particle, we would add them. So when I started my studies, the first edition I had was the second one, I think the sort of light green one. And I was fascinated by all the particles that were discovered. And when I did my thesis, I suffered a lot with the red edition. You can see it on the book there. And then I was very proud to have my discoveries then included in the next edition. Now we have moved on to spiral editions. As you see, the 3 first are not and the others are. And that created controversy because there were different teams, spiral teams or non-spiral teams. Now, to come back to our matter and antimatter, do they behave the same way? That's our whole question. So before going into experimental detail, I wanted to use pop culture as an explanation or an analogy, because you've probably heard of antimatter in films or at the movies. So when I prepared this presentation, I looked at IMDb, so the film repertoire on the internet, and I see that there were many films that included antimatter, and I think they started in 1900. I'm not sure what they're worth. I only know one of them, Angels and Demons, and I thought it would be great this evening to use it in order to illustrate the limits of certain science fiction movies. I don't know if you've seen it, but if you haven't, well, I don't particularly recommend it. But what happens is that we have people who are not on the good side, let's say, and they steal the antimatter from the CERN, and then they want to do crazy things with it. So my objective, I set myself the objective of looking at the watching the movie again, but really I didn't find the courage. So I found a little extract on YouTube that was 5 or 6 minutes long, and it was great because I could see all the scenes where they were stealing antimatter, and that was great because I decided I could use it in order to illustrate my point. We see that little few defects. So first of all, the fact that they used CERN was upsetting because I work on that experiment and they didn't film it at CERN at all. Well, never mind. Visually, it's a beautiful experiment, so of course I understand. But then, of course, well, that probably happens to you when you watch Dr. House, right? And you're a doctor and you see that things are erroneous. So here there are things that are completely wrong. So physicists are wearing white blouses, for example, which you probably know is not the case today. And then there are other mistakes that are quite funny. But anyway, what they do is they create collisions. And then they say, well, we can't create antimatter with collisions. And I'll come back to that later because that's wrong. And then what they do is they manage to isolate antimatter. You see the 3 lights there on the screen. Well, that corresponds to the antimatter. And then this person comes in and steals one of them and puts them in a suitcase, and I will show you why this is impossible. And then they also say that they stole 1/4 gram of antimatter. Now, I'm not good at mental maths, but I'm sure that this is impossible because we've never managed to make 1/4 gram of antimatter, at least not at CERN. So why does this story not work at all is because when we have a matter particle and it's going to meet an antimatter particle, well, annihilation takes place, so they cancel each other. It's a phenomenon that you've probably heard about. You imagine I have the antimatter here. It's a little positron. So the partner the electrons partner or anti-electrons partner, and when it meets up with a particle of matter, what's going to happen is annihilation is going to take place and create two photons. So you see that what's difficult is to create antimatter and to maintain it or to store it long enough to be able to actually carry out experiments on it. Now, to come back to medicine, when we work on fundamental physics, we sometimes wonder if what we do is useful. And sometimes it's very difficult to understand what it's going to be useful for, because when we work on fundamental physics, we feel like it's not very useful other than for understanding what physics is, the universe we live in, which, of course, is a prestigious objective. But I wanted to show you this example. So the tomography through the emission of positrons. So what happens is we give patients a very small molecule that they have to swallow, and it's a little radioactive, so it's going to emit positrons that are going to come across the electrons that are in the body, and that is going to create these two photons. And then we can use this tomography, so this machine, in order to study the brain, for example. So here you have an example of a healthy brain, the one with more red, and the one on the right, which is actually not a healthy brain because there's not enough red in it. So if one day you are asked what physics is used for, well, it's also used in medicine. Now we're going to go into the details of some experiments in order to see how we test antimatter. Well, first of all, we have gravity, which everybody knows about, the apple that falls. And I have to say that when I told this to my daughter, she asked me if Isaac Newton had eaten the apple for his tea, because you mustn't waste things. And I said, of course. Now, of course, the thing that we want to test, when we test gravity and antimatter, if we create antimatter, will it experience gravity the same way? So is our matter particle is going to fall down with antimatter? Is it going to fall up, if I may allow myself? Well, there's an experiment at CERN that's called the alpha experiment that tests just that. And so here is just a simplified linear version of the experiment, but it collects antiprotons. Everybody knows what this is now. It collects positrons, which now you know what these are, and it's going to cool them down and compress them for a certain time in order to create antihydrogen. And then with this antihydrogen, we have only very little, but sufficient for the experiment. We are going to drop them and see what happens. And when we carry out the experiment and carry out the measurements, then we free the antihydrogen. So that's to give you an idea of a publication of scientific work. So this is the collaboration that we did. We carry out all the measurements, and what we observed was that the antimatter seems to behave the same way as matter when it comes to gravity. So it falls just like matter. So there's not much difference there.
Let's take another example that might be a bit more complicated. I have said that symmetries in charge, parity, and time could be combined. CPT, and there is something that allows to combine all three. And when we combine all three, from a theoretical point of view, this tells us that mass, weight, if you wish, and the lifetime of particle will be identical. There are several ways of doing this test, and the easiest one is to create particles of matter. Here counts. A kaon is a particle that contains a weird quark, the S quark we have seen earlier, and lighter quarks. What you see here is that we've measured the difference in between a kaon particle and an antiparticle. And there you can see that there is a difference at 10 to the power minus 19, meaning 10 and then 19 zeros, meaning that we have tested experimentally that in the limit of the precision of the tools we have right now, we don't see a difference in mass and matter and antimatter. So we see that CP and T symmetry is preserved. CPT symmetry is preserved, and this means that the theory of the standard model is everywhere, and it uses this principle. And there are other models that try to play with CP or T that are not preserved, but they are very few. And here we have this that has been experimentally confirmed. We also say that we trust in the fact that those three symmetries put together are conserved and that things run smoothly. I have said earlier that we could play with the combination of the different symmetries. So, since the three together need to be preserved, this means that, well, we need to ask ourselves what happens if we take two and then we don't have conservation. One of the symmetries that interest us is symmetry in time. And we want to see if antimatter behaves in a different way. And so it's a bit complicated to test that, but we can see if C and P together are conserved or not. So how do we do that? The lab we use on the physics of particle uses quark. We generate collisions. I will show you how that works. And then we interest ourselves in the weak interactions. Earlier we've talked about the difference in matter and antimatter and the interaction with gravity, but here we'll talk about something else. And as physicists who work on experiments, we try to test everything in as many systems as possible. When I talk about a system, well, we have this standard model and we try to combine everything we can. We can put a C quark with something else and so on and so forth. So we create many different elements and we try to see if there are differences. How do we do that? First, we try to create antimatter. But how? Well, we proceed to creating collisions between particles, and I will give you an example of a collider. And we have particles that enter in collision, protons, for example, and we use this equation from Einstein. I guess you recognize the picture, who says that there is an equivalence between energy and mass. So we have protons, and then the energy can be transformed in other particles. And some colleagues do tests and they try to find new particles and they try to generate new particles that go beyond the standard model. We have collisions and we try to see what happens. What instrument do we use to do those collisions? If I can change my slide, there we go. It is the LHC, the collider we have just around the corner. It is an accelerator of particles where protons are confronted to huge amounts of energy, and then we have collisions at several places. So if you have the opportunity, you should attend one of the exhibits on the colliders. There are many workshops, and all of this allows you, well, to learn a bit more about this. So this is the instrument we use, and at all these points of interactions we have sensors that allow us to measure things. So we generate those particles thanks to the LHC. How does it work? We have protons. And I may have not said it, but Daniel told it yesterday. Protons are made out of quarks. And so at the LHC we put protons into collisions, and we have also seen that quarks inside the protons were U's and D's. We also know that this is a strong interaction that allows them to stick together, and this is thanks to the gluons. It's this kind of soup you see on the screen. The gluons cannot disintegrate because they are inside, they are confined, they are kept together. The quarks are kept together through the gluons. And so here you see two, but in fact there are many packages, if you will, of those protons. So we take the gluon of one proton that will meet the gluon of another proton. This phenomenon is, well, gluon fusion. Once we have a fusion of gluons, we can generate many particles. If I take a step back, when we do this fusion, well, we can create quarks. Here, for example, we can create a quark and an an anti-quark. This is an example of how we can create antimatter in our colliders. I've taken, well, the B quark because it has quite nice properties to study the difference between matter and antimatter. Then there is another property for those quarks. In nature, we never find them by themselves, isolated. They are always want to enter other atoms, and that's what will happen. And this is hadronization through quarks. So we have all these particles that will be created, and it is by studying those particles we have that we try to understand the differences. Obviously, we need instruments to do all of this. Instruments to be able to measure that and to understand the differences and to build analysis and then obviously build even more instruments. Let me give you an example of an instrument. This is the instrument with which I work, the LHCb, and actually I realized that the xylophone of my daughter truly looks like the LHCb. Here do you see the place where we have, well, the blue the blue line. There we can have the collision for the vertex detector. What's a vertex? It's a place where we have the collision. Then I won't enter into details. We could talk about them during the Q&A. The rest of the instruments provide us different information on the particles that are created at the first step. So it's a bit as in a Sherlock Holmes play. We have detectors and sub-detectors that tell us, well, the particle that went through has this load, this charge, and it had this mass or that energy. We combine all the data in order to say that we've had a collision, that we have observed this and that. This is how we work. And in reality, it looks like this. And this is the R detector at the LHCb at point 8, because I told you there are different interaction points. This is point 8. And here you have a picture of the product of the disintegration. So FYI, other pictures here, and you can see that things are very complex when it comes to the particles of physics of particles at high energy. Because we have many particles, and sometimes we think there are only one or two, but actually we create hundreds of collisions. And so one of the challenges and one of our missions is to try to, well, separate everything and make a distinction in between things so that we can interest ourselves to the particles that are only interesting to ourselves. We will call signal particles the particles in which we are interested, and the other ones are qualified differently. For those who are interested in relativity, well, we take energy and the impulsion, and we have quadrivectors. We combine those quadrivectors, and that's how we can see the particles. So now you will have to trust me, because I will skip a few steps and I will show you what one of the results look like. And this is a result that was shown last week during a seminar at CERN. And we also presented it yesterday. So this is the result. Obviously, it might seem a bit difficult. Indeed, many things happened. But there you can remember one thing from this slide. On the one hand, we created a particle of matter, and on the other hand, a particle of antimatter. And we've been able to ID them and to count them. And here you can see, well, that there is a difference in height. There is one that is bigger than the other one. It is crystal clear. You can see it on the screen, and this is very nice. You have an example of how we can study the difference between both, thanks to the weak interaction between matter and antimatter. Here you have a draft paper. I put draft because it hasn't been published yet, but this is an example of what a paper looks like. And thanks to the CP symmetry, matter and antimatter do not behave the same way. And I have told you that C, P, and T need to be preserved, all three. And here, this is another way we can say that the particles do not behave the same time without T. And it is very nice to be able to test all of that. Now you will tell me, but what about baryogenesis then? Well, we had that amount, and what I can tell you is that we are able to measure through our experiments the differences between matter and antimatter. Nowadays, we measure through our experiments what is predicted in the standard models, but the quantities are too tiny in order to be able to explain baryogenesis. If you want to explain the complete disappearance of antimatter, so we will need to be smart to find other tests. We are almost done. Did you understand everything about matter and antimatter? Well, no, obviously not. There are still many things we all need to understand. We need to work on experiments, work with theoretical physicists to do even nicer things, try them out and discover even nicer things. Now, dear public, I will let you answer the question. Do you think that Alice's rabbit is made out of antimatter? Thank you very much. Thank you, Yasmine, for this conference. Crystal clear and very nice pictures. You are a physicist, but you also like drawing, and these were actually your pictures. Thank you also for stressing how much, well, antimatter is dear to pop culture. It looks like, well, the industry of culture could be interesting, just like medicine is to physicists. But let's get back to physics, and let's try to go through the looking glass. I will now invite on stage the speakers from the other evenings, the ones who work on theory. I want to invite Jean-Philippe Uzan from the Astrophysics Institute of Paris. You've listened to him on Monday, and this is my seat. And then Ed Copeland from the Institute of Physics in Nottingham, and he will take the floor tomorrow and talk about the history of the universe, its past, its present, and its future. Welcome, Ed. Please take a seat. That one. Thank you. And we will have a chat in English and French. And everything will be simultaneously interpreted thanks to the headsets you have and the interpreters working behind the scenes. So just speak freely in your preferred language. Before we take the questions from the public, I would like to start with a tour de table of 5 minutes. And let's bounce back on Paul Dirac, this physicist you mentioned earlier, who in 1931 talked about physics and said that it was more important to have beauty in one's equation than to have them fit experiment.
It's more important to have beauty in one's equation than to have them fit experimentally.
So my question is the following, and this builds a bridge with what you have said yesterday after Daniel Bauman's conference on the fact that we didn't have to forget about experiments whenever we talked about physics. And so when it comes to the discovery of antimatter, the antimatter that is produced naturally in tiny amounts, how is this mechanism different from what you do at CERN? Do you still hear me? Okay, wonderful. So Paul Dirac, when I was a student, I was fascinated by him, and I think that, I think that theory shouldn't maybe be what's most beautiful, because as we've said yesterday, if we want to make progress, and make science progress, generally speaking, it is important to have theories that you are able to test experimentally. And what's more, it is important to have experiments and measurements that feed theory to make more progress, to put it simply. To answer the second question on antimatter, we can find antimatter in nature, namely with some isotopes that emit positrons. We saw the example of positron emission topography, but then there are other examples, and my colleagues who are astrophysicists know that better. There are some astrophysical phenomena where we can create tiny particles of antimatter, antiprotons, and so on and so forth, also positrons. And then, well, we can have predictions of the different flows and we can compare them with experiments. And this is very interesting because we've talked about the standard model and we try to go beyond it in order to understand more fundamental things. And we have models for new physics with dark matter and so on that tell us that we can have some production of antimatter and antimatter, yes. So we have this complementarity and we try to study what comes from space, antimatter we produce in our labs, and I talked about one example only, proton collision, but actually we can have other types of collisions as well. And depending on the systems we use, we can replicate different things that happen, for example, in astrophysics. Well, thank you very much. I think we'll bounce back on those other means of showing antimatter. And now I would like to have a look at your colleagues. Do you want to add something on the mechanisms that lead to creation of antimatter naturally, so to say, maybe in the stars? Well, actually, this is the same as in labs. There are different phenomena with very high energy in the primitive universe, or if you take a dark hole, well, the matter is accelerated, and it is always EMC square. We can read it both ways, meaning that energy can be extracted from the protons to create antimatter, and thanks to the matter, well, there is a creation of energy. We use this for the stars in power plants, nuclear power plants. This formula is fundamental because it shows us that mass and energy are not two different concepts as we learn it. Those are actually two sides of one same coin. It's a tool and also a measurement tool. As soon as we have very intense phenomena with collisions in astrophysics, we create antimatter. But generally speaking, this antimatter doesn't go that far away because there are clouds of gases all around it. We could have maybe luckily one particle of antimatter that goes away and that can go through galaxy, or can become interstellar, but it's very, very tiny, even tinier than in labs. And then what's more, we don't know the initial state. You take two systems that are well known, two protons, and then you measure all the particles stemming from these protons. You have after and before. We never know what happens in between. We have those two pictures, and we have a theory. We try to understand what we cannot record thanks to the beginning and the finishing shot. But in astrophysics, we don't have the beginning shot. And so we have these measurements, and yes, we could detect antiparticle particles, but it is more important to understand the rationale behind what we cannot observe. Yes, so we have an additional tool, so to say, that allows us to check that indeed what's happening in the colliders is also true in the universe, because the universe is kind of similar. Well, the universe in the past was at a very high energy level, and we could build a link with what you've just said about antimatter. If you take a cube of 1 square centimeter, there are 411 particles of light. We do know that it has been measured precisely. We've said it yesterday, and I think Ed will repeat it tomorrow. The universe is expanding. So if you go back in time, well, the density of photons in 1 cubic centimeter will increase. And at one point, the energy will be such that it will be beyond the mass of the electron. And then E equal mc2 enters into play. And in this thermic bath, you will have particles and antiparticles. So if you go back in time, if you measure all the photons, you see that in the past, there should have been antimatter, and the state you have shown, well, demonstrates that the quantity was almost the same, but there was a difference at the 9th decimal. So if we've had millions of times more, we could say it's like that. There, it's almost equal, just at 1/1,000,000th. So it's not the same. It's a tiny gap between equality in matter and antimatter in the universe. This is your observation, and things have been checked. You do see that relativity and physics of particle is respected, and in astrophysics we know that we have those 411, and thanks to cosmology we can go back in time. We need to put everything together, and we see that all the pieces of the puzzle don't go well together, and we miss some pieces. Thank you. We will talk about cosmology in this puzzle, and Professor Copland's conference of tomorrow. He will talk about the history of the universe.
And he will go back to one of its earliest phases, the nucleosynthesis, where the nuclei that will lead to atoms formation have been formed. And would you like to go a bit deeper about this previous phase of baryogenesis? How did it happen? What happened between nucleosynthesis at the end and baryogenesis?
You have 2 minutes.
I'm so glad she has a question to you.
Sorry, it's a hard one.
Je lui donne le micro.
I'll hand him the mic.
I've got the easy question. Nucleosynthesis is sort of the formation of the nuclei that we're all made of. It's about, of order a minute after the Big Bang. It's very important that there wasn't too much antimatter around at that time, okay? Because if there was, then for every nucleus you formed, you'd get rid of it again by annihilating with the antimatter. So the antimatter, this baryon asymmetry, where the number of baryons became higher than the number of antibaryons, had to happen a lot earlier. Now, we don't know really when it happened, and there are models as to when it could have happened, and most of them suggest it happens around the time of the electroweak phase transition. And those are called leptogenesis type models. And why leptogenesis? Because they involve the leptons, which Yasmine was telling us about, the electrons, the muons, the taus. And so we think there should be a difference. There needs to be a difference between the number of leptons and the number of antileptons, the number of electrons and the number of positrons. And as you heard earlier, that's an incredibly small difference. Basically, for every billion leptons, there must be, for every billion positrons, there need to be 1,000,000,001 electrons in order to make sure we ended up with more matter. So the leptogenesis involves interactions with the leptons that could have occurred at the electroweak scale. Baryogenesis, as the name suggests, involves interactions with the baryons. So what are the baryons? You're full of baryons. Well, you're full of leptons as well, but you're full of protons and neutrons. And they're baryons. When 3 quarks combine to give you, that's a baryon. And there are scenarios in which you can generate matter asymmetry using baryons, and that's thought to occur. It can occur at the electroweak scale, but it could also occur much earlier at the grand unification scale, so much higher energies. And there it could involve things like black holes. I've written papers where I have shown how to get the baryon asymmetry out, and with black holes. well, I haven't proven it, because we can never quite prove it. So we always have to make certain assumptions in these calculations, because they're very, very difficult. But in answer to your question, it's a long-winded answer, but it has to occur very, very early on, way before the first second.
Thank you very much. So there are still many things to discover. On va repasser sur...
Let's switch back to French before we give the floor to the audience. I have a question to you, Jean-Philippe. I remember a conference maybe 10 years ago at the Florence Festival. You said that antimatter, like many other physical constructs, imagined long before they were demonstrated experimentally, shined through their absence. Could you build on this idea? Oh, well, I think this is quite poetic, isn't it? Oh, I forgot the details of that conference. So, yes, indeed, we also always try to play with words in French, so shine by one's absence. But so that's what happens in physics. You know, we've been talking since Monday about, and especially yesterday during Daniel's presentation, about those quantities we keep and about symmetries and the fact that next to each symmetry we have a certain quantity. And in many physical systems, we see that at one point, for example, in your experiments, we don't really know what happens, but we see what happens after the experiment. And we try to ask ourselves, is what we had before and afterwards coherent? Did we keep all the amounts and quantities we should have kept? And more often than not, it hasn't been the case, and this has allowed us to discover many things in physics. There is a historic case with cobalt. Cobalt that is disintegrated in nickel, if I'm not mistaken, and it emits one electron. And don't say it, don't say it. You weren't supposed to know it. So we were in 1930, cobalt is disintegrated in nickel, and it emits an electron. And we observe one thing, this particle emits another particle. And you know how it works with a boat. If you put it backwards, it goes backwards. But there, the principle was violated. So the conservation of energy was violated. We had an idea of the mass that we should have had. Then we had a look at other quantities you could have talked about. The leptonic charge, to know if it was a lepton or anti-lepton, and actually there weren't leptons at the beginning, there was only one in the end, and so we needed one lepton, and so antiparticles. And then the preservation of quantity of movement, we needed a certain spin. So we had all the idea, but we hadn't measured that particle. If the theory was true, to have the preservation of all quantities, there had to be an antifermion with a certain mass, and the preservation of the electric mass meant we needed something neutral. So we could build an experiment to find this particle, but we had to believe that the quantity was preserved, and this led to a huge debate. Niels Bohr tried to say that maybe energy wasn't preserved. He built a quantum theory where energy wasn't preserved, but Gaudy said that no, this is important, this is more fundamental than what we know in these particles. There has to be a particle, and so we talked about an antineutrino back in the day, and then it was discovered in 1956. We needed some time to detect this with proper equipment. There have been many discoveries we could anticipate, and this is very important. When you believe in laws of physics, well, these laws of physics are instruments that allow you what you cannot see with the measurement instruments you have right now. And this is also important to build new instruments. And in astrophysics, we always use that. We, for example, talk about black matter. We aren't able to see with telescopes, but they are detected because they are revealed and because no one can hide from gravitation.
Wow, that's amazing. And it's true that serendipity in research is fertile, but probably has its limits in terms of fundamental physics, at least. Now I will turn to the audience. Do you have questions for our audience? If you do, this is your moment. If not, oh, I see a hand up here. Here on the left, can someone give our listener a mic? Good evening. Good evening. I'm from Geneva and the world. In fact, I have a very simple question. For many years, and still today, when you introduce the presentation, sorry, I forgot your name, of the Big Bang, but you as a scientist and those who are with you, what is Big Bang? What is the Big Bang? Who can explain that, please? I'm going to give the floor to my colleague because he's the expert. He works on cosmology and he knows. That is the discipline that works on these first moments of the universe and the Big Bang. So I'm sorry, but this is yours.
Did you get the question in English? Okay.
The Big Bang is sort of conventionally thought of as being sort of the start of our universe. It's where the matter is created, and it's as Daniel was saying yesterday, you think of it as a moment in time. Space is there, and it's a moment in time, and the matter is created and begins to evolve, move apart. But one of the big questions is what banged, right? That's to give us the Big Bang, and we don't know the answer to that. We don't know what caused the universe to actually start. There is another way that you can think about the Big Bang, which I'll refer to briefly tomorrow. But that's the conventional way, that it's the very start. And in reality, at that moment, our equations break down because they actually go singular. The curvatures of our universe become so large that we can't trust Einstein's equations. And actually, it allows me just to point out that so many people believe that this is a reason why we need to modify Einstein's general theory of relativity in this regime, because it sort of predicts its own demise at the very start of the universe. And so what Einstein's gravitational theory doesn't include is quantum mechanics. And quantum mechanics, as we've been hearing today, tells us about the physics of the very small. And so the hope is that by combining quantum mechanics and general relativity into an area called quantum gravity, that will help us understand what really went on at the beginning. You'll have to come tomorrow if you want more details.
Voilà, thank you very much. Donc, voilà le message. Déjà, on a...
Thank you very much. So there's the message. So yes, come back tomorrow if you want to know more. I'm going to turn to my colleague. Do you have questions online? Yes, many have come through. Two are about astrophysics and then one about fundamental physics. So the two astrophysics questions are, could we find galaxies, antimatter galaxies very far away? And the second is, what is or what could be the relationship between matter and antimatter on the one hand, and matter and black matter on the other hand? And in terms of fundamental physics, how do we know that the three symmetries, the CPT, put together have to be preserved? The floor is yours. Wow, these are very interesting and key questions. Who would like to answer? Right, I can provide part of an answer. Well, so for the CPT, three together, there's one side that comes from the theory. And so we have tools that allow us to encode what we know about particles and their interactions according to how we transcribe this. And these are terms that have to be the same. And these are the elements that we have to preserve in order for the theory to be maintained. And I'm sure that my colleagues can add to that. And then, in terms of experiments, the way that we test this is that we produce matter particles and antimatter particles, and then we measure their lifespan. We measure their mass, And what we observe is that within the limit of the precision of the instruments that we use, of course, and the quantity of data that we have, you always have to take that into account, precision. What we observe is that they have the same weight and the same lifespan. So that's a consequence of the fact that we have to have CPT symmetry and preserve it. So that's to answer the last question. Does one of you want to say more?
I'll have a go at the first. So that's a very sensible question about galaxies and antimatter galaxies, if you like, because if there's antimatter out there, how do we know that there isn't a big region of antimatter forming a galaxy? And so, but now imagine if there were, and they met each other, right? It doesn't take much of an imagination to think that's going to be quite a big explosion. And so one of the things that is the people that are looking, say, at the cosmic microwave background radiation bit, which is looking at our observable universe back at when it was only 300,000 years old, and then looking at the light that has come from it since then, they look for these regions. They look in the cosmic microwave background, and they look for sort of really, if you like, bright regions that would be the interface of the matter and the antimatter annihilating one another, and they don't see it. So they're able to put constraints on how many antimatter galaxies there can possibly be, given that they don't see any evidence of them. And then there was a question, I think, which was about differentiating between matter and dark matter. I think you called it black matter, but I'm guessing that you mean what I would call dark matter. And the idea behind dark matter is that it interacts gravitationally just like all matter does, and just like Yasmine was showing with antimatter, it behaves in the same way, but it does not interact electromagnetically. That's the big difference. That's why it's so difficult to detect. And so tomorrow you'll see, hopefully, I'll show you something that Jean-Philippe talked about there, that was you infer the existence of the dark matter by looking at the bending of light. So in the dark matter, there could be a lot of it, and then just as with a lens of a glass, if light goes through it, it will bend, and you look for that distortion. And in fact, there are experts here at the University of Geneva who do this, understand the calculations that are involved. You can infer what the distribution of the dark matter is. But the primary difference between interactions of dark matter and matter is that dark matter does not interact electromagnetically.
Thank you. Okay, merci beaucoup. Je vais rebondir avec une question.
Thank you very much. I'm going to come back to a question that is for Yasmine. So you work on the LHCb in CERN, and CERN is currently in its third phase of exploitation, I think, from what I understand, intensive exploration. And the idea is to try and understand what are you trying to prove regarding antimatter currently? Like, what are the results that you're expecting to find? Right, so the way the CERN experiments work, so the LHC experiments, so we have runs, so long periods during which we collect data. So data collection started in 2009, and we've had 2 LHC runs. So for the LHCb, these past few years, we have done what we call an update. So we removed elements from the detector, we replaced them by more precise tools and instruments, and we changed many things. In fact, I can make publicity for my husband who works in that field. He does it very well. But what we've done, we upgraded the detector, and now we're going to have more data, and we have more precise instruments, and so we're going to be able to combine more data, which means reduce the statistical uncertainties improve precision, and that means that with more precisions, we will be able to observe more effects and more precisely. So with all of this combined, what we hope is that we will be able to have more profound and more precise studies. To give you a simple example, at the end of my presentation, I had the peaks that I show you, the peaks of matter and antimatter, that went up to a certain height. And the height of those peaks will give you an illustration of the size of the samples that we managed to collect and rebuild. But if we have more data, that will enable us to be more precise and go higher, and perhaps we'll be able to see effects that are even more subtle. So, of course, statistically, if you produce more antimatter, well, beyond producing more, the fact is you manage to study it better. Yes, we managed to identify, rebuild them better, and we use tools that are very highly sophisticated, state-of-the-art. We can talk about it if you like, to be able to collect more data, and we hope better data. Yes, of course, data is at the heart of all of this, and a very experiment indeed. Do we have any questions from the audience? Yes, here in the fourth row. Thank you. I have a very straightforward question. It has two aspects. So first of all, you showed us that you've created antihydrogen at CERN. So my first question is, do these antihydrogen atoms combine together in order to create molecules of hydrogen? And is it possible to observe this? And did we go beyond that? Beyond hydrogen? Do we have heavier atoms? Do we have heavier anti-atoms, if I may say it that way, that were observed thanks to your experiments? That's an excellent question, but I'm not an expert. So the experiment I talked about, the alpha experiment, creates antihydrogen atoms by using positrons and antiprotons. And I think that there are other experiments that try and combine these further in order to create an antideuterium nuclei or something. But I think it's possible, and I think it's been done, but I really can't say any more because it's not my expertise at all. I don't know if my colleagues know anything about that. Otherwise, you can come to me and we can try and look into it further. No, it's a fascinating question. Thank you.
So I don't know about the anti-deuterium, but so in the UK, I think it's Professor Charlton at Swansea who's been involved in some of this, and they use the antihydrogen. I mean, it's an obvious thing to try and do, test the laws of physics. The laws of physics still hold when you've got anti-atoms, right? We don't know. We simply do not know whether all the beautiful symmetries that Daniel told us about yesterday, whether they're still valid. If you had a universe that was just made of and so that your question really is very pertinent. I mean, to be able to build up more complex atoms and molecules to test just interactions between them and see if the ones that I know about all still coincide. All the interactions still are what you would expect for standard matter, but I don't know very much about it.
Oui, merci pour votre question. Du coup, un bon axe de recherche.
Thank you very much. This is very interesting for upcoming research. And this leads me to a question for Yasmine. You talked about the alpha experiment earlier that allowed to demonstrate that gravity was applied similarly on matter and antimatter. I think that the alpha experiment also studied the spectral nature of matter and antimatter, meaning that matter is supposed to send light a certain way, and so does antimatter behave the same way? Everything we know for now is that the only place where we are able to see difference between matter and antimatter is on the weak interaction, that's where we see tiny differences. Then when it comes to gravity interaction, electromagnetic interaction, everything that explains, the emission, the different states, everything seems to behave the same way. Okay. So gravity is similar, and for the spectral, light spectral, same, and strong interaction as well. Okay, thank you very much. Thierry, do we have other interesting questions? If we imagine ourselves in the future in our region, there is a question. What would the new accelerator at CERN bring? This accelerator physicists want. And if we go a bit further, why do we always aim at having bigger and stronger machines? Won't we in the end reach a certain limit, maybe an intellectual limit, maybe a physical limit? It looks like the next step is always further. So that's quite a challenging question. I don't know who raised it, and thank you for raising it. So let's recontextualize things. The LHC I have just shown has a circumference of 27 kilometers, and it is in France and in Switzerland. Today, we wonder if we should build another one that would be 100 kilometers. You can imagine the size of this instrument. It would be an FCC, and there we would be able to do two things. One, we would be able to accelerate electrons, one electron and an anti-electron, and this would be interesting because, well, from what we know, the electron is a particle that is quite punctual, whereas the proton is made out of many different things. So when we have collisions of electrons and anti-electrons or of protons, we can learn different things. Then there is the question of the usefulness of these tools, and this is quite challenging, and everyone wonders. I think that nowadays, well, these questions are on fire, because at the LHC we have discovered another boson and different particles from spectroscopy, so we did expect them to be there, but we haven't seen any new particles. So actually there are things we need to be able to understand, and so we wonder if this accelerator is the answer in order to understand these things. If I need to be honest with you, well, I don't know if it is the best answer. We are asking this to ourselves, and then as people who are doing experimental physics, we wonder if it is the best way. It is something we know quite well, something we can push forward, but nowadays we don't know if there are other ways of doing things. So all of this to say that this question is legitimate from a physical and technological point of view. Obviously, if we need engineers to build such a tunnel, well, it needs quite a lot of means. And then there is the question in society, will we discover things? We might be more lucky. At LHC, we could maybe have discovered something new, and then there wouldn't be any ambiguity. But for now, things are in this gray area. We understand many things. We need to understand more, but we try to make progress. What's the best instrument to make progress? That's a question. Indeed, it is a question that I had also asked, I think, when we prepped here. So thank you for raising this question online. It is true, those accelerators are in a country, and they require international collaboration, and it is not because it is in Geneva or Japan that we only have Swiss or Japanese researchers. And now I would like to ask you a question. Are there other ways of working on antimatter experimental means, maybe, without using these colliders? I think we have neutrino detectors that allow, well, to demonstrate some things on antimatter. Maybe you could tell us a bit more about, well, other means to study antimatter. So indeed, there are many experiments, many ways of testing all of this. We do like the colliders because, well, we have this equation from Einstein. We know very well we can put a lot of energy and create new particles. Then we can also study neutrinos and antineutrinos, those that come simply from the sun and other places in the universe. But for that we need instruments. For example, in Japan, they have an instrument, the Super Kamiokande, like a big pool. Imagine a big pool with many sensors on the sides. And these photomultiplicators, well, will see the neutrinos or antineutrinos that from time to another will interact with these sensors, and we can then study this. The approach is a bit different, and that's what my colleague said earlier. We do like the colliders because, well, we can truly control the energy, what we do, the way we reproduce experiments. When we do neutrino experiments, we can also do some with beams, also thanks to nuclear plants, and also with astrophysics. So all of this is complementary to each other. The field of neutrino is immense. It is a very different field where we learn different things from what we do here, for example. Well, thank you. Thank you very much. Do you want to add something, Ed or Jean-Philippe?
Maybe one thing, which is that there are other ways that people look for evidence of CP violation and their consequences, and they don't all involve accelerators. There's one that I used to be at Sussex University, and there they had a very eminent group that would look at the neutron, just the little neutron. And neutrons are like little magnets, as are protons. And so if you apply a magnetic field, they'll move around, and because they react. So it's a particular quantity that can be looked for. It's called the electric dipole moment of the neutron, and it's just effectively the flip of the neutron. And it's with protons and with neutrons, they both have them, and it's part of the reason the MRI scanners work, that some of you may know from hospitals. So there are predictions you can make from a theory that there should be, if there's a given amount of CP violation, then you should see this electric dipole moment of the neutron. It should have a non-zero value. And the value that is currently constrained, if I remember, in suitable units is about 10 to the minus 26. So it's less than 10 to the minus 26. That's 0.00000000001. So a really very near to zero. And so they're once again putting constraints on the amount of CP violation that there is out there based on these experiments. That's a table. Well, the electric dipole moment's not a tabletop one. There's another one called the electron electric dipole moment, and that's a tabletop experiment that you can do.
Thank you.
Well, thank you. There are many different and complementary ways of studying the asymmetry between matter and antimatter. Do you have some more time for one or two questions from the public or from in the internet? Do we have questions here in the room? I don't see you. Oh, there we go. Let's hand the microphone over. Okay, thank you. Actually, I had a question for Madam. Thank you for your presentation. If I understood you properly, you talked about the rupture in symmetry, and I didn't really get what you said about a hypothesis or something that had been observed. An example, I don't know. Could you maybe explain that again? Well, thank you. In order to answer your question, in the standard model from a theoretical point of view, we have some tools that allow us to describe if, for example, we are interested in the quark, how the interactions in between quarks happen. And we have this CKM matrix, and this allows us to understand how quarks interact. And through that matrix, we have a phasis that tells us that we have the possibility to not have a rupture in symmetry between matter and antimatter because of the weak interaction. So from a theoretical point of view, we say that this should exist, but then we, in the experiment, we produce quarks that hadronize. We create particles of matter and antimatter, and then we test the interactions, and we are truly able to create links depending on the interactions and to create links with the matrix. And currently I'm working on an experiment where we study the matrix. And we test this out, and we do see that it works very well. This matrix allows us to have a given quantity of asymmetry, and what we measure seems to be aligned with that. And we continue studying this because, well, this quantity we measure is too tiny to explain the asymmetry we need in order to go back to the Big Bang. So another way of putting things is we could say that the standard model has this type of interaction and allows for that quantity of asymmetry. And if we have a new type of physics, new interactions, there too, would we have a certain quantity? Would we have a certain leeway? Maybe more difference between matter and antimatter? Question mark. This is how how we try to find new interactions, and this is what research beyond the standard model is all about. I hope this answers your question, and thank you very much. I thought there was another hand. Yes, there we go. And unfortunately, we won't have much more time left. Let's try maybe one or two more questions. Sorry, and thank you. One final question for me. To Jean-Philippe Uzan. You said, if I'm not mistaken, that first we have laws, mathematical and logical laws, and that physics, empirical physics, tries through the laws to fill the gaps, things we don't know yet. But couldn't we do things other way around? Couldn't we have empirical physics leading to developing laws? This is my first question. And then, next to that, we have Hoffman from MIT, who said that with the Max Planck constant, 10 power 33, there is a paradigm, there is a space-time paradigm that disappears, collapses. What does he mean? And is this understandable? When I said that we used laws, I meant that at one point, well, there are laws that we deem for granted because of all the experiments carried out. And so we don't have any evidence against the law, and so we don't put them into question. And as soon as we find discrepancies, anomalies, we wonder if there is something missing. And so we keep them, but we try to build on them. And I don't want to oppose myself to Dirac, I'm not at the level, but I could ask Heinemann what he thought about that. But whether the theory is beautiful or not, whether we are smart or not, famous or not, if the theory is not aligned with the experiment, well, then it's wrong. And so we need to know what we do afterwards, because a theory might present some issues, but until the last experiment, it was correct. So at least it was a good approximation of the new theory we need to develop. And I quoted Einstein. He said there was no logical pathway. There is an intuition that is developed next to experiment. And this comes from all the theories we spent time on building. And through physics and astrophysics, we've always seen how we found solutions. We talked about matter earlier. Well, in the evolution of the dynamic of the solar system, at the beginning of the 20th century, there was an issue, and because of analyzing all the ways of putting another planet that could explain the trajectory of Mercury, well, we moved on to relativist theory. And so, indeed, in the aftermath, we will tell you something in a logical way and differently, but I am deeply convinced that when we do research and when we raise questions, well, at one point, we are not always rational. We try out things, we have an intuition, and as soon as we find a pathway, we make it logical, we make a theory, and we can give this theory to our fellow colleagues so that they can say, well, there is this or that doesn't go round, and then we can share the theory with the experimentalists so that they try it out. So we need to have the freedom not to be coherent at one point in time, because if not, we cannot make progress, and it can be challenging sometimes. I know there are a few texts that touched me, the one of Einstein in 1905 on the fact that light could be built out of particles, because he started by saying, we do know it's a wave, everyone says it, Maxwell, everyone says it, all experiments show it, and Newton demonstrates that it doesn't work, but he said, allow me for this article to suppose that it is possible. And then he went on and made discoveries. So taking some freedom is key. Sometimes you are scared because there is a community. We know all the arguments that lead us to thinking that the hypothesis is stupid, but from time to time we do need to explore other pathways that may seem to be out of reach, because maybe there it is possible, well, to find another way forward to make progress, and there is maybe something someone has never seen before. And all scientists can be as good as all of the others, and sometimes one says, well, let's try things differently. This is related, well, to, well, luck as well. There are many possibilities, and one day one can be lucky, but that's about it. And physics of anomalies will show us much more, and this is exciting. Where is the solution? Should we review the structure of space and time? There are arguments in quantum gravity and in mechanics that allow us to explore this pathway, but we don't have any consistent and coherent theory that allow us to explore this. So I don't know. I don't have the solution, but day in, day out, we try to make progress. I hope this provides some kind of answer. Thank you. Indeed, we shouldn't try to tell the end of the story before we take the freedom, the liberty of going where no man has never gone before. Thank you. Thank you to all of three. Let's give a round of applause to our speakers. Before we finish tonight, two reminders. We have the light and music show every evening until November the 17th at the Museum of Art and History. If you haven't gone there, well, it's every evening at 6:30, 7:30, 8:30. It's 20 minutes. It's for free. Second reminder, our journey through the symmetries is not done yet. We will continue tomorrow at 6:30 with Professor Ed Copeland. We will talk about the present, the past, and the future of the universe, its expansion and dark energy. It's a vast topic. I wish you a lovely evening and see you tomorrow. The interpreters wish you a lovely evening.